Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
To be talking about the finding of liquid water on Mars. So the big surprise to find liquid water on Mars is that it's extremely cold there. So how can you have liquid water? In the only possible way if you have a powerful antifreeze like the ones that we use on the road here in Michigan during the winter. I'm going to give a little background on this mission, Phoenix. What are the mission goals? Talk a little bit about the spacecraft and the landing site. Why do we land where we land on Mars? Was in the Martian Arctic, and why did we go there? What's interesting about it? And then about entry, descent, and landing on Mars. This is the most difficult phase of those missions. And so far, about 50% of our missions to Mars failed, and most of them during this phase. And for me, as a scientist and engineer, this is the most exciting phase of the mission. So I had a grad student working on that, and this discovery of liquid water, in fact, was a byproduct of us trying to understand what was going to happen during the landing. And then those salts, there's antifreeze on Mars. There was evidence in the literature for those salts on Mars, but we didn't know for sure if there were any where we were landing. And then about this process, the liquescence is when you go to a restaurant and you try to put salt in your food, usually it doesn't come out easily. And it's because salt absorbs water from the air, even when the humidity is very low. Many times with humidity below 10%, they absorb water, and they absorb water and melt into a liquid. And this process is called the liquescence. So I'm going to talk a little bit about that. And then what's the big deal about liquid water on Mars? And the big deal is that we are looking for, the main goal of space exploration is to look for life beyond Earth. And on Earth, every place that there is liquid water, so far we found life. Doesn't matter how acid, how basic, how saline, how cold, we always find evidence for life. Then if we want to look for life elsewhere, the first thing is to look for liquid water. And then some conclusions. So the background, the goal of the Phoenix mission was to study the history of water and the chemistry of the topsoil on Mars. We call the soil Mars regolith because there is no organic matter as far as we know. And to find out if the landing site could support life. If we had some bacteria from Earth and took it there, would they be able to survive in that place or not? And the mission was divided in 4 team groups. One related to the atmosphere, that I was the leader of this group. One related to the physical properties of the soil, another in the chemistry of the soil, and another one that's a combination of all those is to find out what's the potential for the soils to sustain life. So why follow the water? I mentioned this in the beginning because water is essential for life as we know it. And on Earth, everywhere that we see liquid water, we find life, including one of my favorites here, deep cave, more than 3 miles down in a cave in South Africa, with a microbe was discovered where the source of energy is the radioactive decay of the rocks. So the microbes is living there just because there is a tiny bit of water in the rocks. And it's not a chain of microbes, a single microbe that live independent in this environment. And more recent, another very exciting, was in a glacier, below a glacier in Antarctica. In the spring, cracks in the ice, there's some water that falls, and there is lake under this glacier because it's very saline, the water is liquid, and it's a few million years old, and there are bacterial life in this water. So here's the Phoenix lander. It's about maybe the science deck the center of the lander here is about the size of this desk, and then 2 solar panels on the side, and doesn't move. You see, doesn't have wheels, just land and stay in a single place, and has a robot arm. Doesn't have wheels because the main goal of the mission was to dig down and look at what was happening below the surface, and could dig about a half a meter below the surface. And then there is a camera here, stereo cameras, simulating what a person would see at the surface of Mars. It's about 2 meters above the ground, and the distance between lands is like the distance between your eyes. It's really simulated geologists at the surface of Mars. And then there's a LiDAR here that's like this green laser pointing up, and then you look at dust and clouds in the atmosphere scattering the LiDAR. And then meteorology, little tower here with temperature and wind sensors. And then the main instrument was really this box here, has 6 little containers that we can take sample of soils, put into this instrument, and then heat it up and look at the gas coming out as a function of temperature. That's how we detect the water. It's water from the mass spectrometer associated with this instrument. And then as we heat, we also see transitions of phase. And then there is another instrument, this black box here, that has a microscope that we could look at the soil samples in detail, and has 4 wet chemistry lab where we mix the soil with water that we brought from Earth, and we look at the wet chemistry of that soil, and that's how we discover the salts. Let's see, what else? Oh, the robot arm has a camera at the tip here that we took some of the, I think, most interesting pictures with it. Here to give you an idea of the size, the spacecraft being assembled at Lockheed Martin, just outside Denver, Colorado. And it was launched on August 4, 2007 at 5:30 a.m. Out of Kennedy Space Flight Center in Florida. And arrived on Mars May 25th, 2008, 4:40 p.m. from our control center that was in Tucson, Arizona, the Science Control Center. The landing site now. Phoenix landed right there, about 6 to 8 degrees north, and Mars is really high terrain in the south hemisphere and low terrain in the north hemisphere. And the topography is amazing compared to the Earth. For example, the highest mountain in the solar system is Mount Olympus here, and it's about 20 miles high. So Mount Everest would be very small compared to it. And this crater here in the center has about, I think I forgot exactly, about 4,000 kilometers in diameter, and about 4 kilometers deep. So everything's really dramatic. And one of the reasons for that is because Mars is smaller than Earth, the gravity acceleration is smaller, so it's easier to create big things. And there's less erosion because it's very dry climate, and there's no rainfall. And there is little evidence of some early in the history of Mars producing some of the big channels here, like you see this one, that would make the Grand Canyon be a miniature. This would be like the Grand Canyon going over across the entire United States. So the topography for Mars is really amazing. And here, another view of the landing site. Phoenix landed there. So here is the North Polar Cap of Mars. And what we are seeing here is water ice. The polar cap, it's covered by CO2 or dry ice during the winter, and during the summer, the remaining here is water ice. And there is a big canyon here that's also about 4 kilometers deep, and the dark stuff around it are sand dunes. Because of the large temperature contrast between the polar cap here and the surrounding region in the spring, there is very strong winds always blowing around. And then the end of the Phoenix mission was cold air rushing down this canyon, lifting lots of dust here. The dust moving around went over the Phoenix site, and Phoenix was powered by solar energy. So we had very little solar power, and we are still trying to do too much science. And the battery discharged, and the Phoenix was never able to recover from that discharging of the batteries. So the reason for landing there, where Phoenix landed, is that the Mars Odyssey, a spacecraft around Mars, found out lots of hydrogen in the soil. Here's a map of hydrogen. The green means 50% of the topsoil, about a meter of soil, by mass would be, if that hydrogen was in the form of water, that would be 50% of the mass of the soil would be water ice. And here in the polar cap, 100%. And so we landed there because there was evidence for lots of hydrogen in the soil that we assume it was water ice. And the goal of the mission was to check if it was really water ice below a thin layer of soil. And if that water had melted in the past, that would make that region habitable. Here's another picture of the landing site from after Phoenix was, I think it was about a year before Phoenix was launched. There was this Mars, I forgot the name of the mission, has a high resolution camera called HiRISE that has, can take pictures with a resolution of about 5 centimeters, 2 inches. And so we're starting mapping the site that we were planning to land. And if you look carefully in this image, you see some black dots. Those black dots are shadows of boulders of about 5 to 10 meters in diameter. So the landing site that we had originally chosen was uniformly covered by those boulders. So if it were not for this mission, Phoenix had probably crashed. And so, but we were able to find a place where there was much less boulder, like this region. But since you don't control the landing, it's always a big risk because it could land on top of one of those boulders. Then it's the end of the mission before it started. So this entry, descent, and landing, I think I have a little short movie here. So since it's so difficult, and it takes 7 minutes to go from the top of the atmosphere at 12,000 miles per hour, if everything is right. 7 minutes later, you'll be at the surface at 0 miles per hour. And everything's automatic, and there's nothing that we can do because it takes much longer for the signal to go from Earth to Mars. So all that we can do is just to wait and cheer. And it's very, very exciting because at this point we had worked on this mission for 7 years. So, and everything is down to the 7 minutes. So the sequence of events here, it's arriving at the top of the atmosphere at, as I said, 12,000 miles per hour. Then the speed is decreased by a factor of 10 by just the spacecraft burning. It's like covered by a protective coating, and that coating is being burned and removing the heat of the spacecraft. So that reduced the speed by a factor of 10. Then a parachute opens, the spacecraft still going at supersonic speed, and then decrease the velocity by another factor of 10. And in the case of Phoenix, then there is a radar that detects the distance from the surface, and at about a little less than a kilometer above the surface, it released the lander, and the lander has 12 rocket engines. And those 12 rocket engines are very simple, And the way that control power is by controlling the pulse cycle. It's on and off, on and off. And I'll show you this acceleration. Here is time along this axis, and here is acceleration. The first big acceleration is just by friction with the atmosphere. So the spacecraft is really fast here, but there is no atmosphere, so there is no deceleration. Then the spacecraft velocity is slowly decreasing, but the density of the air is increasing. So the peak acceleration is here, and it's about 8.6 Earth Gs, so 8.6 times the acceleration of gravity on Earth. Then it goes down because the air is becoming more and more dense, but the spacecraft is slowing down. And then right here, the parachute opens. Then it's a big jerk, and another 8.6 Gs. And then the landing legs are deployed, so it's also produce an acceleration of about 4 Gs. And then right here, the rocket engine turns on. And because to control power, you control just the duty cycle, how much the engine is on and off. The spacecraft is really shaking hard. And then the touchdown was here, about 4 Gs. Okay? So this, one of the engineers at JPL had this idea that this spacecraft that had the high-resolution camera is going to be used as the communication link between Phoenix descending and Earth. So the radio signal from Phoenix goes to the spacecraft, and the spacecraft sends it back to Earth. Since it had this very high-resolution cameras, one of the engineers said, why don't we point the camera towards Phoenix and take some pictures of it landing? And I think most people thought this guy was crazy. How can you do that? Both spacecrafts are moving at thousands of miles per hour. And so here's one of the pictures. This is a big crater. Phoenix landed, I think, 10 miles ahead of this crater, and the crater is about 30 miles in diameter. And if you look carefully here, you see something. What's that? Anyone can guess? Exactly, it's Phoenix on the parachute. And now I have a little animation, show the spacecraft with the high-resolution camera pointing, Phoenix coming, take a snapshot, a few, and now you look at it. And I'll do a little animation done by NASA JPL. So Phoenix is ahead of the crater, but just because of the perspective, looks like it's landing inside the crater. That would be the end of the mission. So this is the first picture of a spacecraft landing another planet. So here's that crater. It's the other way around. The crater is about 10 kilometers in diameter, and Phoenix landed about 30 kilometers away from it. So here is Phoenix. And now the landing. What I was interested in, one of my students was working at his PhD thesis, was to look at the interaction of these rocket plumes with the surface, and to find out what are the properties of the soil of Mars that we can learn by just the fact that we'll be landing and perturbing the soil. And there are two parameters that we want to calculate. One is the cohesion between soil particles, and the other is the porosity of the soil. So I'll talk a little bit about that. So here was our approach. This is the spacecraft, if you're looking from the top, and you'd see the rocket engines coming in pairs, 12 rocket engines. And we did a simulator of the rocket engines, but instead of burning fuel, we just put gas at high pressure, simulating the pressure in the combustion chamber. And then we built only 2 of the engines, and because of symmetry, we built this plane of symmetry, and we had a sandbox here, and our goal was to eject this plume into the soil with a range of properties that would cover the range that we expect on Mars, and find out what we could learn. And the interesting thing is that if Phoenix were landing on the moon, then because there is no atmosphere, the exhaust gas would expand, and the impingement at the surface would be very benign. If Phoenix were landing on Earth, because the air is very dense, then the rocket plume would diffuse, and the interaction with the surface would be very benign. But the density of the air at the surface of Mars is about 1% of the one at the surface of the Earth. So it's not enough for the gas to diffuse, and it avoids that it expands. And so the plume is very collimated and very long. And this is our numerical simulation showing that. So from 2 meters above the surface, the impingement at the surface would produce supersonic flow at the surface. The contours here are Mach numbers. Mach 1 means 1 time speed of the sound. So here it's about 11 times the speed of sound. But you can see the blue here, it's more than 1. So it's your supersonic flow. And what we found out is that because the rocket engine is pulsating, between pulse, the gas penetrates at the soil, then the soil is semi-permeable. Between pulse, the soil starts expanding. When that happens, the soil behaves as a fluid. So the next pulse comes, and you can create shock waves, like you see like in a faucet. If you have a plate below, you open the water, that shock wave that forms is a very, very powerful process for producing erosion. And here it's showing that. We see this shock wave. It's like a supersonic wave moving across the soil. This is 0.3 seconds after the interaction started. Here's 0.8 seconds, means that the deepest soils that we could imagine above ice would be removed in less time than it would take this interaction that would last about 2 seconds. Here's a little movie showing that at about 1,000 frames per second. And what I want to show is those shock waves moving across the soil. So let's see, right here, you see? And this process was not known before. We call it explosive erosion, that a pulsating rocket engine can be so efficient in carving the soil. So some people were concerned that maybe that would be dangerous for landing. For us, it was very interesting because that would be a really good soil mechanics experiment. So then from this, what we did is predict what the Phoenix science team was very interested is the soil that's removed from below the lander. Here's distance in one direction, distance in the other direction. He's looking at a quarter of the lander. And blue means soil is being removed, and the green to yellow and red means soil deposited. Means that this area here in gray is the area that the robot arm can reach. This area will be covered by a layer of about 1 centimeter thick of soil that was removed from under the lander. So that was the prediction before we went to Mars. And then the first picture with that camera in the robot arm showed below the lander, we see soil was removed. The ice below the surface was exposed, exactly as we predicted. And what caught my attention was this landing strut with all this stuff here. What was that stuff? We had predicted that in this impingement of the rock plume with the surface, the ice would be exposed below a layer of soil, and that ice would partially melt and be splashed around. So we were expecting to see something like a mud being splashed. So we would see dry mud. But this is interesting because it's not like when you drive over mud and the mud splash on your car. There are some really spheroidal features there. So that was the first very interesting image from Phoenix. And here's just to show you that landing. This is an image of the landing site. They scale here 25 meters. Here's Phoenix. It's bright because the solar panel is reflecting sunlight. That heat shield that was used to decelerate during the entrance to the atmosphere fell out here, and the parachute with the back shell here. So all within, a few hundred meters from the spacecraft. Here is a little movie showing how that image from under the lander was taken. The camera is here in the robot arm. You can see 2 rocket engines here. You can see the rocket engines around the lander. Okay, that's the picture of the ice below the spacecraft. This is interesting because this is the first time that human spacecraft touched ice in another planet. So this was a very famous picture that was cover of many magazines because of that. So the hypothesis here then that during that landing, we removed the topsoil, exposed that subsurface ice. Part of that ice, about 1 millimeter, according to our calculation, melted and was splashed around. But instead of just dry, some spheroidal grew. So how can you do that? The only possible way that we know is from some salt absorbing water from the air and growing as a liquid. So how can we test that hypothesis? So that was, I would say, one of my goals after this in the mission was to really find out what was happening in this thread and trying to test the hypothesis that was a salt absorbing water and forming liquid today on Mars. Here's just an interesting picture since we landed in the Arctic, and the sun never set during the summer. So it's just a sequence of the sun going down close to the horizon, then going back again. And another thing is there is lots of dust in there. So the atmosphere of Mars is really dusty. It's like being in LA in a very polluted day. Now salts on Mars. So there is many evidence in the literature for salts on Mars. We find salts on Mars meteorite, that rocks from Mars that we recover here on Earth. And the idea that salt can produce liquid water on Mars is not new. There is many discussion in the literature going back to the 1970s when people were getting ready for the Viking missions to Mars. And what's interesting about salt, now I just want to go over this diagram, is let's imagine that you're here in Michigan and you fill up your swimming pool with seawater. And then the winter comes. And as it gets colder and colder, what's going to happen is that instead of the water freezing at 0 degrees Celsius, that would be pure water, the saline water freezes at a lower temperature. So for seawater, it's about minus 20 degrees Celsius. And as the water cools down, it goes along this axis here, or this curve. It means as it's going to be cooling down, pure ice is going to be forming, and the remaining liquid will become more and more and more saline, up to a minimum point that, sorry, this is for the seawater. This minimum point is about minus 22 degrees Celsius. And then the remaining salt water would freeze. And that salty water frozen will be less hard than the pure water frozen, and will be more like an ice cream than, really dry ice. And this is what we call the eutectic temperature, and this concentration that's for seawater is about 30% salt, 7% water is the eutectic mixture. So what's interesting about this is if you have a salt on Mars that can produce those eutectic temperature that's above the minimum temperature that we have there today, then you can have liquid today on Mars. And the other thing is that the salt is absorbing water from the air, even when the air is very dry. So even in a very dry planet like Mars, you can have liquid. And especially if you cover it with a thin layer of soil that would avoid sublimation, then you can have liquid almost anywhere on Mars today. So that was what I was looking for. And so, I forgot to say that just imagine that we have the swimming pool here in Michigan, filled with seawater. And we just go through a winter, the water starts cooling down, the ice will precipitating out, and the remaining liquid will become more and more saline, up to a point where that liquid would freeze. And for seawater, that would be minus 22 degrees Celsius. Now, next spring, as the swimming pool starts warming up, the first thing that's going to happen is this saline mixture, frozen, is going to melt. And it's going to melt as soon as the temperature reaches this minus 22 degrees Celsius. Then with all the other ice frozen, you have some liquid. So if you go through many climate cycles like this, then you're going to be separating, the stuff that's more difficult to freeze from the ones that freeze more easily. Then just the fact that Mars is going through climate cycles is doing this naturally. So we should expect to see this most easily melted substance everywhere on Mars. If there is the south and there is the source of water. We know that there is the source of water, and we know there are salts, like on Earth everywhere that you go. In the desert you find salt lakes, right? So the same thing we should expect on Mars. So this is very exciting because it means liquid saline water is possible today almost anywhere on Mars. So now, changing a little bit to the landing site. So we call a day on Mars a sol. It means a solar day. And because a day on Mars is 24 hours and 40 minutes. And this is interesting from the point of view of operation of those missions, because each day we have to work on Mars time. So each day we go to work 40 minutes later. So during the cycle of this mission, you can imagine what happens, people going around the clock, and you can see the change in the mood and the mistakes coming and going. So it's very interesting. So here the mission lasts about 150 days. And, well, maybe the order is a little confusing. So we found, at this point in the mission, after we took the image that I showed, we didn't have any clues of salts on Mars yet. But I thought the evidence of salt was that spheroids and the fact they seem to be absorbing water from the air and growing. And later on, we found two salts there that can freeze the water at very low temperature. One is perchlorate of sodium, and perchlorate of magnesium. Perchlorate of magnesium freezes at about minus 70 degrees Celsius. This is around this curve. And of sodium, about this one. And in black here is the temperature of the air that we measure during the mission. Each excursion here is 1 day on Mars. So you can see during at noon, the temperature is, at the beginning of the mission was about minus 30 degrees Celsius. In the evening, minus 92. And at the mid of the mission, the maximum temperature was minus 25 degrees Celsius, and the minimum towards the end of the mission was almost minus 100 degrees Celsius. So it's really, really cold. And here is a plot of pressure. As I said, the pressure here on Earth, I just noticed that I made an error here in the units, not 8 hectopascal, this is Pascal. On Earth, the pressure is 10 to 5 Pascal. So basically, the pressure is going down, and each cycle here is one diurnal cycle on Mars. And the pressure is going down because winter starts in the south hemisphere, and the atmosphere of Mars starts freezing and forming CO2 ice over the polar caps. So 30% of the atmosphere freezes and becomes part of the polar cap during the winter. Here's a thermodynamic diagram of water, just showing this pressure. Here's temperature. Here's the triple point of water, where you can have water as liquid, vapor, or solid. And on Mars, where we landed, the pressure was around this, means that liquid water is possible, except that it's too cold to have liquid. But the liquid water would not boil. Here's an image of the first clouds that we saw on Mars. There was like puffy clouds moving around. And here's the picture of, with that LiDAR. Here is time, and here is height above the surface. It's basically a cloud forming at about 4 kilometers above the surface. And this is cloud, snow falling and drifting with the wind. So it's the first picture of snow falling in another planet. And here is a picture of cloud forming at about 4 kilometers and fog forming near the surface. So we took the first pictures of fog also forming over the lander. So now where's the evidence for liquid water on Mars? So First, I showed that image from below the lander and the stuff that was splashed on the leg. And now, a trench we are carving, and we are expecting to find ice 10 or 20 centimeters below the surface. And the first trench that we carve, 5 centimeters below the surface, we find this very soft ice. And if you look at the boundary here, very sharp boundary between the ice and the terrain. That really suggests that thing flew as a liquid. And the fact that ice was soft means it was not pure water ice. At those temperatures, you had to have something else, and a salve would make the ice that soft. And the decision here in the mission was to leave this trench alone and let that see what happens as a function of time, and took about 100 days for that ice to disappear, and when it disappeared, it left some white stuff behind. So that's probably salt. And you can see from the length of the shadow here that this layer is about a few millimeters thick. And then here's just a sequence showing carving that trench. And you can see this. I'll go back to that. Okay. So now we have 2 pieces of evidence, those spheroids in the strut and this soft ice. The soft ice is very exciting because in a pristine place, we didn't disturb it during the landing. This was just digging below that layer of material that was disturbed during the landing process. And this is in a region where it was covered by a thin layer of material that was removed from below the lander. In contrast, I have a little joke here. This is another trench. You guys know the monolith? So my joke during the mission was that we discovered the 3rd monolith. It was buried in the landing site because this is another trench, and this is after the robot arm trying to sample it at full pressure, scooping hundreds of times, and we could not remove anything. Look at the ice here. Looks completely different from the other ice. And I think this is pure water ice that was formed in the pores of the soil. And it was deeper and very, very hard. In order to remove samples, to look with that, the thermo-evolved gas analyzer that's melting it and look at the gas coming out, we found out that this is really water ice. And to remove, we had to use a little tool that's like a cheese grater that you can see here, because the ice was very, very, very hard. So what I explained in the beginning, the liquid sense is the self-absorbing water from the air and melting into a liquid, and that can happen when the humidity of the air is well below saturation with respect to water, and can happen at temperature well below 0 degrees Celsius. For perchlorate of magnesium, it's minus 70 degrees Celsius. I'll skip this. So now looking more closely, so we took a sequence of images of that lander strut, but we didn't take too many because that robot arm was the busiest instrument of the mission. So there is big competition among 50 scientists to use it. So you can use only when no one else is using, or it's a big battle to decide what's going to be done the next day. And the main goal of the mission were to look for the samples of the soil, analyze the chemistry of it. But looking closer, this was 8 days after we landed, another image of that strut, and now we had a very high quality image, and you can see one of these spheroids really, it's like you expect a water droplet. We did a stability analysis. On Mars, you can have droplets that are about 3 centimeters in diameter, more than an inch and a half, over a flat surface. And it's much larger than on Earth because the gravity acceleration is small on Mars. And because it's very cold, the surface tension on water is also much higher. And in a vertical wall, they can be more than 1 centimeter in diameter and still not drip. The interesting thing about this image is that you see those different things in the lander, different size and different brightness. And this one is brighter around and dark in the center. And those salt absorbing water from the air release heat. So even if they start partially freezing, that would appear brighter, the center stay liquid longer and appear to be darker. And here's a lab experiment showing that. We have this perchlorate of sodium absorbing water from the air, forming this frost layer. This is to show two things. If we had frost forming here, we should expect a smooth cover everywhere. It would not form spheroids. And then if you wait enough time, in this case was a few hours, this salt absorb the water, release heat, and melt the ice, and the liquid area appears to be darker. Now, I'll show a sequence of 3 images. One is 8 days after we landed. This was 31 days after we landed. This one 44. And I'll go back and show a few things. First, this is spheroidal. This one is darker around. Now, this one is much darker. So that's what you expect if completely melts. And now disappeared. So that's what you expect if it drips, right? Except that on Mars, we cannot take images every second and take very high quality image. You have to work with what we have. And another interesting thing, there are 3 little things here. They grow and they stop. Now, one thing that we can do quantitatively is to look at the size of those spheroids and calculate the growth rate and compare with what we expect from theories of salts absorbing water from the air. And we did that, and they all agree with it. So in contrast, this was, if we look right below the landing strut here, that ice that was exposed is sublimating. If we look at the center image here, we can see that 21 days after we landed, and then 73 days after we landed, that ice is changing because it's losing mass to the air, was exposed to the dry atmosphere. But the stuff in the leg is growing. So it could not be ice because the colder ice under the lander is sublimating, and that strut is warmer, and I'll show, I think, next. Well, let me divide this in the evidence for liquid. First, what we call the physical evidence. They move, drip, and merge. There is a change in relative brightness that you expect from liquid and partially freezing and completely melting. They have the right shape, and their maximum size agrees what we expect. The one that grows the largest, it's the one that disappeared, so probably drip. And the thermodynamic evidence that I'm going to show some of the calculations next, they grow only on dark material, so it's probably the salt mixed with soil. And the growth rate is what we predicted by the theory. And the one that disappeared, nothing else grows there. So if we remove the salt, then there is nothing to absorb water from the air. You shouldn't expect any growth there. So everything is consistent. And they grow in a strut that's warmer than the ice that we can see is sublimating. So it could not be ice growing there. And then I'll show at the end. So towards the end of the mission, start getting colder. And when it gets colder, if we had the swimming pool experiment here in Michigan, without snow falling on top of the swimming pool, as it gets colder in the winter, the pure water ice would sublimate because the air is not saturated, and the remaining saline ice would stay there. So it's a way of filtering this out. So that we didn't expect to see this in the strut, so there was no really controlled experiment there. But Lockheed Martin that built the lander, so I discussed with one of the engineers, they are looking for temperature sensors that we could use to find out what the temperature of the strut was. And we find a temperature sensor just at the top of the strut in a fuel line there. And then they turn it on, but as you can see, it takes a long time to do those things, to find and to get all the permissions to turn it on. It was turned on 60 days after we landed. And in black here, it's the data from that temperature sensor. And then what we did was to estimate the temperature where the spheroids are located. The temperature at the top is warmer because of all the electronics there, and we know the temperature of the ice. Then we can estimate the temperature there is between the two. And this is the red. And at this point, we had the red analyzed the soil and discovered those perchlorates of sodium and magnesium in a few percent biomass in the soil. That's quite a lot. And those melt at the temperature that I put here. Perchlorate of sodium melt at this temperature, perchlorate of magnesium at this temperature. And if you mix different salts, you can lower further the temperature. So that means that in that strud, during the diurnal cycle of the mission, we could have liquid of those two salts. And here's the humidity of the air, just showing that humidity, huge fraction of the day. Here's time of the day. Here's humidity, 100%, 50%. Part of the day was above 50%, and those salts absorb water from the air when the temperature is above 50%. So you could really have them growing by absorbing water from the air. I'll skip, I can talk to anyone after the lecture on this, but our simple model describing what was going on, it's basically water from that sublimating ice and the air being absorbed by the salts and producing those liquid in the strud. And here, the calculation that I mentioned, if you look at the radius of, let's say we start with a chunk of salt, and we look at the radius of that chunk of salt as it absorbs water from the air as a function of the humidity of the air. So if you increase the humidity of the air by a threshold, all particles are going to increase in volume proportional to that initial volume and the change in humidity. So we check if all those spheroids that we saw growing would be obeying this law, and they were. So that was Phoenix. And then, since then, we have been looking for other evidence. Maybe it's possible really to have liquid water there on Mars now, and looking at other ways of detecting it. And one is to look at brightness. I'll just mention this really briefly. This is our lab experiment showing that brightness is a reasonable way of measuring the liquid, and I'll just focus on this. This is one of the spheroids that we show growing here. And the red here means that's according to this quantitative photometric analysis, liquid, and green yellow is partially frozen, but still mostly liquid. Ice would be bright this way. I'll skip those. We also checked that one possible thing was that what we were seeing was an effect of contamination from the rocket engines during the landing. And we can discount that idea. And now the most interesting thing towards the end of the mission, it's getting really cold. We can see frost forming everywhere. And now we start taking more pictures of the strud. It's so complicated to do this because we don't have a camera with automatic exposure like on Earth. What we do, we take images and we look at them, and we are not happy, we change, take another one. So as the conditions change, it's really difficult to get a very good quality picture. But we took some really good one at the end of the mission, and I just want to point out that it gets colder, and we start seeing frost forming at the surface around the lander. What happened in the strud is exactly what you expect from the saline water absorbing humidity from the air. They start disappearing because now they freeze. If they freeze, the ice sublimates, and what remains is small pockets of that very, very saline water. And we can see here, for example, very dark. That means it's still liquid. Initially, we thought this image was even that some missing pixel in the image, and we check it's not. It's really real. So that's exactly what you expect. Now going back to the beginning, remember that first range, only 5 centimeters deep, where the ice would be unstable there, would be sublimating into the air. But a saline mixture would be stable. And this chunk of ice from that layer that's millimeter thick, cylinder removal, it means it was scooped like an ice cream, and the sharp front. So this is all evidence for the same behavior in unperturbed soil on Mars. So now, more recently, we have been looking at images of the polar region of Mars, and we see these streaks forming the spring. And here is a sequence of one. So what do you guys think that is? You can look at the temperature here. I'll show one more time if I can. Okay, I'll skip. So we look at another way. How can we check if those things are liquid on Mars? First, we look at brightness, and according to our brightness, it's really liquid. And forming the spring, basically, it's a sand dune in the polar region of Mars, close to where Phoenix landed, all covered by frost. As the sun starts warming the surface, that frost starts melting, and this thing it's like a flow of water. And then it gets warmer and warmer, it disappears. So if that was this liquid saline water, it means the water would evaporate, and what's left is the bright salt behind. That's what we see here. But this is not a proof. But then we came up with another simple idea. If you look at the brightness at different colors, like the top here is ice. Ice is as bright in the blue-green region as in the reddish region. If you take an image in those two colors, we chose those because this high-resolution camera in orbit around Mars has image in those colors. If you look at the Mars soil, it's brighter in the infrared than in the blue-green. And if you look at those liquid, it's the other way around. It's brighter in the blue-green than in the near-infrared. So we can calculate a parameter. I always skip the explanation why this is the case. If we had liquid on Mars, we can define a parameter where is the difference in brightness normalized by the brightness in one of those colors. For liquid, this parameter should be between -8 and -6. For snow ice, between -1.5 and 0. And for Mars soil, between 0.5 and 1. Even for the darkest soil on Mars that we can find. And so there's no overlap. So if we have those images, then we can really look for water on Mars. And we did that. Here's one sequence, the color image, the blue-green image, and the near-infrared image. So look at this. Remember that thing that we saw flowing down? So now we look. Here is, for me, was the most amazing image. We see the sand dune. This is early in the spring. Everything's covered by frost. The brightness here is frost. The reddish is Mars soil. So this is a slope because the sun is shining up on the slope. So the slope is defrosted. And then this thing forms. And we see 3 weeks later, the front is propagating. And those big puddles on Mars, more than 25 meters in diameter. And I think this is really the proof of liquid water lasting only a few weeks after the frost is starting getting warmed by the sun in the spring in the polar region of Mars. And here's more on that. Now, just to finish, astrobiological implications. There are bacteria on Earth that thrive in those highly saline waters. You know, we think of the Dead Sea as being too saline for life, but there are bacteria thriving in the Dead Sea. And those bacteria are called halophilic, bacteria that love salt. Here's that glacier in Antarctica that I mentioned. What's interesting is that there is liquid below this glacier because it's a highly saline water, and it's also very rich in iron, like Mars. And cracks in the ice in the spring produce those waterfalls. As soon as the water starts flowing down, because it's rich in iron, it rusts. So it has the color of rust. And because of that, it's called blood falls. And the water is 1.5 million years old, and there are bacteria living there. No solar radiation, not everything isolated, and there is life there. So then it's very likely that life could exist on Mars also in the similar conditions. In the bottom of the oceans, because saline water is heavier than the fresh water, there are pools of really salty water, and there's big chains of life thriving in those conditions. And so one of my current projects is really to understand this and to understand how we can form those pockets of liquid water on Mars today, and if life is possible in those conditions, starting with bacteria on Earth that we know are happy to live in those conditions. Conclusion. So there are many independent physical and thermodynamic evidence that liquid saline water is present in the areas disturbed by the Phoenix lander. That's my view. The evidence is overwhelming. Not everyone agrees. And this is consistent with the results of lab experiments. I didn't mention that, but we also did a bunch of lab experiments that really confirm that. And that layered ice discovered in one of the trenches is really evidence for this liquid saline water today on Mars. And the more recent spectral data that I just showed really confirm that, unexpected for us, you can have this liquid saline water at the surface of Mars for a few weeks every spring. Now, if you have a thin layer of soil above it, then it could probably stay liquid the whole year around. And this is important because it has implications for life. So the end with a little joke. The theme of NASA today is to follow the water. So I have a little joke here. So follow the liquid water. So, okay.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.